The first example where this was used is for proving a Bertini theorem for over finite fields. So let me begin by reminding you what the classical Bertini theorem is. So, okay. All right, so suppose I have a smooth variety. So actually, there are many Bertini theorems, but I'm going to talk about the Bertini smoothness theorem. So I'll start with a smooth quasi-projective variety in Pn. Okay. Say of dimension m. So over some ground field. So then I want to know that there exists some hyperplane. I would like to say that there's a hyperplane that cuts x smoothly, so that the intersection of the hyperplane and x is also smooth. And not only that there exists one, but that most hyperplanes should have that property. And you can quantify what most means by looking at the space of all hyperplanes, which is a dual projective space. So maybe I'll denote it Pn dual. I mean, it's really just another projective space, but I'll think of its points as corresponding to, so a point in here corresponds to a hyperplane in the original Pn, namely the one defined by the equation given by those coefficients. And so when I say most hyperplanes have the property, I mean there should be at least a Zariski dense open subset of such points. So, okay, so the conclusion is that there exists a dense open U inside this space of hyperplanes such that each U in U corresponds to a hyperplane H. So it's going to be a hyperplane then defined over the residue field of that point. So U is a scheme point. Little u is a scheme point. And then the key property that I wanted to have is that the intersection, H intersect X, should be smooth. Smooth of dimension m minus 1 then. Okay, so that's the theorem. Now, you could ask, okay, now given that you have this dense open subset, can you actually find a hyperplane that's good in the sense that it cuts it smoothly, defined over the same field as defined over K? And for this, well, if K is infinite, so then there's no problem. So if K is infinite, well, then you can say, yes, there exists an H defined over K such that H intersect X is smooth. And the proof is simply that if you have that the K rational points in this case are dense in the projective space. So in particular, U must have at least one K point. Okay, so on the other hand, this argument doesn't work if K is finite. And in fact, not only does the argument not work, but the conclusion can fail. If K is finite, then there are only finitely many hyperplanes you can try. And it can happen that every single hyperplane is tangent to X. So, okay. Yeah, so this corollary can fail. So if K is a finite field, say, the field of Q elements. So because of this, Nick Katz asked the following question. Well, there are two possible ways you could solve this problem. One would be to enlarge the ground field, and then of course you can do it because the Bertini theorem is true over FP bar. But the other way you could try to resolve this is to ask whether there exists not a hyperplane but a hypersurface of higher degree. So hypersurface H in Pn. So, but over K. So which is now, from now on, it's going to be this field FQ, finite field. Does there always exist a hypersurface such that H intersect X is smooth? Because now, again, even though you're restricting the ground field, you still have infinitely many to try, and so there's some hope. So this is a question he asked, and the answer is yes. And this is one of the theorems I'm going to prove. So so the answer is yes, and this was proved by me and also independently by Ofer Gaber. Okay, so and actually what I'm going to prove is a lot more. Not only does there exist such a hypersurface, but if you choose a hypersurface sort of at random, so I'll make sense what that means. If you choose a hypersurface at random, then it has a positive probability of being good in the sense that its intersection with X is smooth.
Is your proof and Gaber's proof the same?
No, not, well, they're similarities, but they're not the same. I mean, so yeah, so sorry? Yeah, in some ways, yeah. For example, so he proves that for certain degrees you can find such a hypersurface. And so the result I'm about to state will show that for all sufficiently large degrees you will have such a hypersurface. And not only that, but also I'll get a positive fraction. So asymptotically as the degree goes to infinity. Okay, so let me state this result. Let me see. Now does this go all the way up? Okay, so let me state now the theorem. So this is going to be the Bertini theorem over FQ, over finite field. So I need to introduce some notation. So first, S will be the homogeneous coordinate ring of Pn. And so, okay, so Pn is proj S. And SD will denote the subset of the homogeneous polynomials of degree D. Inside S. And S homogeneous will denote all of these, so it's the union over D. And now, and now for each homogeneous polynomial, so you can let's say in FSD, you can define you get the hypersurface that it cuts out. So this will be, so as a scheme, it's a proj of S mod F. So that's just the hypersurface F equals 0 inside Pn. And now what I need to do in order to state this theorem in a quantitative way, because I want to say that a positive fraction of hypersurfaces have the good property, I need to say I need to define the density of a subset. So a density of a subset of the homogeneous polynomials. So the density of a subset P in S homogeneous, is that legible from where you are? Okay. No? Well, it says of a subset P is in S homogeneous. Okay. So I'll denote by mu of P, and it'll be defined as the limit as D tends to infinity of the number of homogeneous polynomials of degree D, the fraction of homogeneous polynomials of degree D that satisfy the condition. So I mean, as I said before, there are only finitely many of each given degree. So I want to take how many of them satisfy the property P, and then look at that fraction as D goes to infinity. And the other thing I'll need in order to state the theorem is just to remind you what the zeta function is. So I'm assuming this has come up plenty of times in the summer school. Yeah? So, okay, yeah, so there's a question. I mean, this might not exist. Okay, so maybe I should say if this exists. Yeah, you could also define the same. If I replace the lim by a lim sup or a lim inf, then it would exist. And then I'll put probably an upper bar or a lower bar in order to denote those upper density and lower density. Yeah. So part of the theorem I'm going to state is that for the set I'm talking about, the density does exist. Sorry. What? You could do that as well, but I guess this is actually stronger than. Well, it's about the same actually because it's almost the same because the number of. Most of the polynomials of degree up to d have degree d. So not 100%, but a good, almost asymptotically 100%, I guess. So as long as the dimension of the projective space is not really tiny. Okay, so so you could stay it that way as well if you preferred. Okay, so let me just remind you quickly what the zeta function of a variety is. So define the zeta function. So I'm going to use so there are two versions. One is in terms of, if you write in terms of s, or you can write in terms of the or q to the minus s. So it's a rational function in q to the minus s, and it's given by, there are two definitions of it. One in terms of the Euler product, which is going to be the one that's relevant for me. So maybe I'll just give this one. So you take the product over the closed points of x of 1 minus the size of the residue field, which is q to the, I'll write the size of the residue field as q to the degree of p, this raised to the minus s, and then the whole thing inverse. Oh, I just realized that's probably not visible to you, but you probably know what the zeta function is anyway. Okay. Okay, so I can now state the theorem. So this is the Bertini theorem over FQ. So it's that, okay, so again, the setup is essentially the same as in the first Bertini theorem. So namely, I'll take, maybe I should lower this so you can, if it's visible. So again, I'll take a smooth quasi-projective subscheme. So, and I'll again let M be the dimension of dimension M over FQ. Yeah, so now I'm over a finite field. And the set I want to measure is the set of homogeneous polynomials such that the corresponding hypersurface intersects X smoothly. So is smooth of dimension m minus 1. So then the conclusion is that the density is the zeta function of x evaluated at the dimension of x plus 1 inverse. So in particular, this is a positive number. So this proves that in particular there exist hypersurfaces. In fact, then it also shows that for all sufficiently large degrees, good hypersurfaces exist. Yeah. So this number, in fact, not only it's a rational number because the zeta function itself is a rational function in q to the minus s, and so it's some number between 0 and 1. Okay, and in fact, it's one interesting thing is that it's actually independent of the embedding of x. It depends only on the isomorphism type of x. So, for example, I mean, just before I get into the proof, let me give an example. Suppose you take x equal to p2, and you take it embedded in p2. Okay, so x is all of p2. So what is this theorem saying now? So if I take p2, so a hypersurface is now a plane curve, and I'm intersecting it with the whole space. So I'm just getting that plane curve, and in fact, let me do this over f2. So then, what this is saying, this theorem is essentially saying that if you take a plane curve at random over f2 of high degree, so that means that then the probability that a plane curve in p2 over f2 is smooth. So I'm putting quotation marks. I mean, the way this is supposed to be interpreted as that density equals 21 over 64. And that's just what comes out if you work out the zeta function of p2. Okay, so any questions about the statement? All right, so now actually before I give you the proof of this theorem, which is going to, I mean, as I said, it's going to use a sieve method. Let me just remind you how a sieve method works on a much easier problem. So, it's an analogous problem. It's almost too easy, but let me do it anyway. So, this is just the question of the density of square-free integers. Yeah, so square-free, integer square-free if it's not divisible by the square of any prime. So, okay. So let me let P be the set of square-free, and let me just look at non-negative integers. Square-free set of square-free natural numbers. So, and the question is, the analogous question would be, what's the density of this? And now, I mean, the density would be defined in the obvious way, namely, you intersect the set with, you look at how many. Look at what fraction of the first n integers belong to the set. Take that limit. So if that limit exists. And the answer, which maybe some of you, well, probably many of you have seen before, is that this density is zeta of 2 inverse, which may look suspiciously like the answer to the other theorem. In fact, this is, and the 2 itself is the dimension of spec z plus 1, if you take Krull dimension. So in fact, this is not just an analogous problem. There's actually a common generalization of this and the Bertini theorem. Maybe I'll discuss it in the second lecture. So maybe you can guess what that would be. Okay, anyway, what I'm going to do now is just explain where this number comes from, and explain then show how the same idea is used to solve this. Well, plus some extra ideas will lead to the proof of the Bertini theorem. Okay, so well, first, before I give a proof even, let me just give the heuristic. So why should the answer be zeta of 2 inverse? So the idea is you start with all the integers, you throw away all the ones that are divisible by 4, you throw away all the ones that are divisible by 9, and you keep going, and you see what's left. Now, if you throw away, now what's the probability that an integer is divisible by 4? Now, I really shouldn't be, I mean, this is heuristic, so I can say whatever I want. Okay. I mean, this is not really a probability in the usual sense. I mean, it's really just density. So that's 1 over, so that's pretty clear. And so what's the probability that n is not divisible by 2 squared? So that should be 1 minus 1 over 2 squared. And so, and what's the probability that it's not, so the not is still there, okay, not divisible by 2 squared or 3 squared? Well, I mean, if you believe that these conditions are independent, and they are by the Chinese remainder theorem, then it should be the product of this with this. And that's actually, so that, okay, so that's, okay, now we want the integers that are not divisible by 2 squared, not divisible by 3 squared, not divisible by 5 squared, and so on. So you should just multiply them all together. And therefore, the answer should be so 1 minus 1 over 2 squared. And that's exactly the inverse of the Euler product for the Riemann zeta function. So that this is exactly this. Okay, so what's wrong with this? Why isn't this a proof yet? Well, I mean, it's true that any finite number of these conditions are independent, and you can figure out the density. But there's something wrong with just taking you can't always just take an infinite product when you have infinitely many conditions. I mean, they're not really all independent. I mean, and in fact, and not only are they not all independent, but I mean, if you look at only integers up to n for some fixed n, then they really aren't independent. For example, numbers from 1 to n are not going to be divisible by a prime bigger than n. Okay, so the way you actually turn this into a proof is to approximate the set we want to measure. So, okay, so this is actually the proof. That was the heuristic. So approximate P by set PR that does not have all the infinitely many conditions, but just conditions for primes up to R. Namely, these will be the almost square-free integers. Namely, the ones that are n is not divisible by P squared for any prime P up to R, less than or equal to R. And so that's going to be a little bit too big. So to get rid of, and then after computing the density of that set, then you want to throw away the set of, let's see, so you want to throw away the set QR, which consists of the integers such that it's divisible by some big prime squared. Is divisible by P squared for some P greater than, for some prime P greater than R. Okay, so yeah, so then in other words, P is equal to P sub R, the set difference, so this minus Q sub R. And then the proof goes, so well then there are two lemmas, so one is, the first one's really easy, namely the density of P sub R. This is easy because P sub R itself is just a union of residue classes. It's a union of arithmetic regressions. And just by the Chinese remainder theorem, you get this. It's what you expect. And then the other part of the proof is to show that when you delete the QR, nothing much changes. Namely, you'd want to show that the upper density of the set QR is small, at least when R is large enough. So, in fact, what you can prove really easily, I'm not going to do it, but you can imagine that's not hard to show. And so now if you combine these two, then it'll imply that the density of P itself will be, if you now let R go to infinity, so it'll imply this is equal to the limit of this density, which is the infinite product. Okay, so are there any questions about that before I move on to the proof of the Bertini theorem? Okay, so so I wanted to use the same idea. Now what's going to be now again, if you want to ask, well, okay, let me do the proof of the Bertini theorem in the special case where, in fact, almost in the special case I just talked about, namely the one I had P2 contained in P2. But actually, let me do even something that's slightly easier. So this is the proof of the Bertini over FQ in the case, okay, so for simplicity, I'm going to look at the case where X is A2, is the affine plane inside P2. It is all over FQ. Okay, so, and I'll identify every homogeneous polynomial with its dehomogenization. So with its, so f, say f1xy, so which is now in fq bracket xy. So now I'm really talking. Now the set P is really the set of f's that define a smooth affine curve. And so to say that it's smooth, that's again, it consists of infinitely many conditions, namely that the curve that f defines should be smooth at each closed point. So smooth means from now on smooth of dimension 1 at each closed point each closed point P of A2 over FQ. Okay, so what does this condition look like? I mean, so this is supposed to be the analog of the condition that is not divisible by P squared. And so I want to impose these infinitely many conditions. And again, I'll do this approximation where I use only finitely many conditions. So what does the condition look like to say smooth? So, well, you all know that if I fix this point P, in A2, then to say that the HF is smooth at P, as you all know, that's just a condition in terms of partial derivatives. So, well, first of all, if the curve doesn't go through P, I'll consider it to be smooth at P. Okay, so first, the only way, so to say that it's smooth means that the partial derivatives, the value in the partial derivatives are not all 0. And where are these? So where are these three values? All three of these values belong to the residue field of P, which is it's the field of size Q raised to the degree of P. So you can now do the same heuristic we had in the square free case. Okay, so namely, let me start. So the heuristic would be if you believe that those values associated, is it visible? If you believe that those three values are sort of uniformly distributed over the residue field, then you can ask, okay, what's the probability that they're all 0? And that should be 1 over the size of the residue field cubed. Okay, so the heuristic then is that the probability that it's smooth at that one point P and this it should be 1 minus 1 over q raised to the 3 degree p. And similarly, and now if you want to impose this condition at all closed points, then again, if they're independent, then so H is smooth at all P in A2. So okay, this is still heuristic, so I can say whatever I want. So it should be, so this equals really maybe should be equal to the product over all closed points of this. And this again is just a special value. It's just the zeta function again, the inverse of the zeta function. So this is where the zeta function comes from in that theorem. This time it's the zeta function of A2 over this finite field. Okay, so let me now start. Okay, so this so far is still heuristic. So let me now try to turn this into a proof. And so this is what I'm going to do for the rest of the rest half hour. So and it's going to be a little bit more. It's going to be a little harder than the square-free integers. So so actually, what I did here, I sort of divide up the primes into two categories. They're the small primes and the big primes. The small primes were the ones up to R, and the big ones were the ones greater than R. And here I'm going to have to break it up into three categories. So, except now the primes, so the primes are replaced by these closed points. The closed points are playing the roles of the primes. So there's a condition at each closed point, and I can measure the size of a closed point by the residue field degree. And so the first category will be the points of low degree. And I'll handle these the same way that I handled the conditions in the square-free integer problem with the small primes. Namely, I'll define P sub R to be the set of F's that define a curve that's smooth as far as the points of low degree are concerned. So namely, it'll be the set of F's such that H of F is smooth at all closed points P of degree less than or equal to R. And what I want to claim about these points, about this set is that that its density is what the heuristic predicts. Namely, it's the product of 1 minus q to the 3 degree of p for the primes for the closed points in A2 of degree less than or equal to R. So this is a finite product, right? So okay, so how do you do this? I mean, it's essentially the same argument as for this lemma, and then namely you use the Chinese remainder theorem. So this is very easy. So namely, so you can if I let M sub p be the maximal ideal of the point P, so it's inside the polynomial ring. So that's the maximal ideal corresponding to P. So then and I let I define I to be the product of MP squared for all the primes P of degree less than or equal to R. So then if I have a polynomial, homogeneous polynomial, I want to test whether it belongs to the set, then that will be true if and only if the image of F under the map So S of D now is really, I can write as sort of the polynomials of total degree up to D, because those are the dehomogenizations of homogeneous polynomials of degree D. And if I map this into this quotient, then that will tell me everything I need to know about whether this defines something as smooth at P or not. Namely, this is isomorphic by the Chinese remainder theorem. This is the same as the product of as this product. So where, again, there's a product over all points of degree less than or equal to r. And to say that it's smooth at a particular point P means that the polynomial does not completely vanish in this factor. So, because to vanish here means that the polynomial vanishes at P and that its partial derivatives vanish. So, okay, so the condition, the condition is that it should be, for it to be smooth, it should be non-zero in each factor over here on the right. So let me give this name. Let me give this a name. Let's call this phi sub d. This is just the reduction modulo I map. And if I want to measure the density of, I want to measure what fraction of polynomials have this property that they don't map, that the image is non-zero in each, that the image is non-zero in each factor. That's really easy to do if you know that this map is surjective. Because then then you can just say, okay, what fraction of elements here in this finite ring, what fraction of elements here are non-zero in each factor? And then that'll give you that product here. So the key point is to know that this thing is surjective. And, well, I mean, it's kind of obvious that it's going to be surjective once D is large enough, because, I mean, this is a finite ring, and if I took the whole polynomial ring, then of course that surjects onto this. So, but actually for later on, I'll need to know a little bit more. For the next, well, for when I deal with points of higher degree, I'll need to make this a little more refined. So what you can actually say is that phi d is surjective. I want to quantify how large D has to be in order for this to be surjective. So it is surjective if D is large, and in fact, it's already good enough to take D greater than or equal to the sort of the codimension of I. So as a vector space. So in fact, you can do with one less. So what's the reason for this? So think about this map as you start increasing D. So as you increase D, the image is going to get larger and larger. And I claim that each time you increase D, it has to grow until it fills up the whole thing. That's just because if I want to go from one D to the next D, I can just take that image, multiply that image by X, multiply it by Y, and also take the original image and add those three things up, and that'll give you the image for D plus 1. Because that's how you can generate polynomials of degree D plus 1 given the polynomials of degree D. So that there's some process that takes the image for a given D and gives you the image for D plus 1. So, and I know that eventually, when I iterate this process, each time eventually I get to the whole thing. Now, if this process got stuck somewhere before it filled up the whole space, it would just be stuck there forever. So what has to happen is that this image grows as D grows, monotonically, strictly increases until it fills up the whole thing. And so the number of steps that I can last is only the dimension of this space. So by the time you get up to the D equal to the dimension, it must have filled up the space already. Maybe I should have written some of that down, but it's not really a big deal. It's not a big part of the argument. So I just want to, okay. So anyway, so it's surjective once D is large enough. So that proves this lemma because, as I said, the fraction of elements here that are non-zero in each factor is exactly the right-hand side of that lemma. So, okay. So the next thing I need to do is, so that's sort of the main term in this that's going to be the approximation. Now what I need to do is show that it's very rare for a plane curve to have a a singular point of high degree. So, okay, and I'll need to break up these points of high degree into two categories. So there'll be the points of medium degree and then the points of high degree. So the points of medium degree I'll define. So these are going to be sets that I'm going to delete from P sub r. Namely, so what do I want to throw out? I want to throw out any polynomial such that it has a singularity at a point of medium degree. And medium degree means, first of all, well, bigger than the ones I've already considered, namely bigger than r. But also medium means it's not too large compared to the degree of the polynomial I'm considering. So at which the curve is not smooth. Okay, so, and now I want to show, so this is supposed to be the error. This is supposed, well, part of the error. This is the error coming from singularities of medium degree. So I want to show that this has small density, at least, well, I don't know that the density exists, but at least the upper density tends to 0 as r tends to infinity. So this is it's the analog of the lemma I erased down here, where the upper density of q sub r was less than or equal to 1 over r in the square-free integer case. Okay, so how do you prove this? So among the polynomials of degree d, how many of them are bad at, how many of them give you a singular curve, a curve that's singular at a particular p? So again, that's going to, it's going to use the fact that this phi sub d map is surjective. If I look at just this one point, so I have this. So for p in this range, this is surjective. So I mean, the reason I put d over 3 here is that the dimension of this space here is 3 times the degree of p. So under this hypothesis, this quotient has dimension at most less than d. And so by the argument I gave before, this will surject onto this. And therefore, if I want to know what fraction of these polynomials have a singularity at p, in other words, which of these polynomials map to 0 here, then that's going to be something that happens with probability exactly 1 over this cube. So 1 over q to the 3 degree of p. And then if I want to add, I need to add that up over all primes. I mean, so the upper density of this q sub r will then be, at most, the sum over all p's in this degree range. So of 1 over 3 the degree of p. I mean, I could have, I mean, this is sort of overcounting a little bit, because there's some f's that might have more than one singularity. But that's okay. I mean, this will give me an upper bound for the number, for the density of f's that has one of these singularities somewhere. And now using the fact that you know how many closed points there are of a given degree on A2. I mean, of degree, yeah. So you can show this actually, even if I were to take this infinite series, it would converge. And so if r is sufficiently large, then this is going to be small. So this is going to tend to 0 as r goes to infinity. Okay, so in the last 15 minutes or so, I now have to do the hard part of the proof, which is the points of high degree. So again, the goal is just to show that it's very rare for a smooth plane curve to have a singularity of high degree. So, okay. So here there's an additional trick. So I mean, so far what I've done is pretty similar to what you would do in the square-free integer case. But the problem is that when the degree is large, the surjectivity I used up there, it fails. I mean, just because if P is huge degree, then the vector space kxy mod mp squared is going to be huge dimension. I mean, and huge even compared to D. But there are not that many polynomials of degree up to D. That's bounded. So it won't be surjective anymore. So you can't exactly estimate the probability of having a singularity at a point of high degree. Oh, the other problem is that there are infinitely many points of high degree, so you can't sum over all of them and hope to get something. Okay, so anyway, so here's what you actually do. In order to, and R will be the things I need to finally delete from P sub R. So I've already deleted the ones that have a singularity at a medium degree point. So now I want to delete the f's or the curves that have a singularity at a high degree point. So a high degree means at least D over 3. So I should take a union over D again. So union over D of again, at which h of f is not smooth. Okay, okay, and what I want to show is that this set has density 0, meaning that it's rare to have for a curve to have a point of a singularity of high degree. So in other words, if I choose f at random among polynomials of degree D, polynomials of degree total degree D, then it should not have a singularity of high degree. So the way I'll generate a random f is in the following funny way. Namely, using this expression. And I'll explain why I'm doing this in a second. So what I'm going to do is I'm going to choose these F0, G1, G2, and H one at a time at random. So for random, F is going to be a polynomial of total degree D. G1 and G2 will be, and H will be polynomials. Okay, let's say G1 and G2 will be polynomials of total degree at most D minus 1 over P, so that the total thing has degree P again. And then H again will be, H will be same thing for D over P. Oh, that's right, yeah. This is supposed to be F0. So I'll choose F0, G1, G2, and H randomly, uniformly and randomly from these sets, from these finite sets. Oh, I should have said K is always FQ, okay? Okay. So, and if you do that, then the distribution of F is also uniform at random, because already you have this random F0 being added into everything. So, sorry, what? Yeah, that's because I'm raising it to the pth power and then multiplying by a degree 1 thing. Yeah, this is a pth power here. Yeah, so P is, okay, I guess I didn't say that either. So P is the residue characteristic. So, okay, so Q is P of A. Okay, so the claim is that if I choose these, first of all, if I choose these F0, G1, G2, H randomly, then this F is a random element, a uniform random element of polynomials of total degree up to D. And that's obvious because even if I condition on H, G2, and G1, then already the fact that F0 is being chosen uniformly at random makes the whole thing random. Now, why did I choose these things in these order? So the point is, I mean, this condition about having a singularity, that's some condition in terms of the partial derivatives of f with respect to x and y and the value of f. And by writing f in this way, I can sort of partially decouple these partial derivatives from each other. For example, if I want to know the derivative with respect to x, I only need to know f0 and g1. Because everything else is a p-th power, has x occurring to a p-th power. And similarly, if I want to know the partial with respect to y, then I only need to know f0 and g2. So I'm going to choose them in this order, f0, g1, g2. All right. Okay, so now what's the probability that, well, I'm going to first choose f0 at random, and then conditioned on that choice. So fixing that choice, what's the probability that G1 is such that the dimension of the locus where the x partial derivative is 0 is at most one-dimensional? Maybe I should have said, what am I trying to do? I want to show that I want it to be true that the locus where f and the partial derivatives are all 0. This is the singular locus. I want that this usually has no singularity of degree greater than or equal to d over 3.
You mean that there's no common solution?
It's okay if it has common solutions as long as those common solutions are points of low degree. I'm trying to rule out I want to bound the probability that there's the singularity of high degree.
Usually has no singularity.
It usually has no singularity of degree greater than or equal to d over 3.
It seems like you're referring to the singularity of that system of equations.
Sorry? Oh, sorry. Yeah, sorry. I see what you're saying. Yeah, sorry. That's not what I wanted to say. It usually has no point. I mean, this set of is the set of singularities. So I want to say this has no close point of. Sorry about that. Okay. So what I'm going to do is first, so I'm going to cut down this set I'm going to add one polynomial at a time and hope that each time I add in a polynomial, the dimension of the space goes down. And then by the time I've added the third one, I hope that there's nothing left, or at least nothing left of high degree. So first, I'm going to put in the condition about the partial derivative with respect to x. And it is true that most of the time, even if I've already fixed f0, well, I mean, then this partial derivative depends only on g1. And most of the time, if you choose g1, this set will be at most one-dimensional. In fact, meaning that it's not the whole space. Because all I need for this to happen is that this polynomial be non-zero. And it's true that most of the time this derivative is not 0, because this derivative is going to depend on this g1 to the p. So in fact, there's only going to be at most one value of g1 that makes this 0. So this is going to be, well, let's just say it's approximately 1. So if d is large, then this is going to be very close to 1. So okay, since I've only a few minutes left, I'm going to be a little more sketchy now, but let me just continue. So now suppose I've chosen f0, and I've chosen one of these good g1s. So I didn't choose that really bad g1 that made this that made this polynomial 0. So suppose that I'm in this situation already, conditioned on a good choice. Meaning good means that it passed the previous test of g. What's the probability that when I put in the next condition, I get something that's at most 0 dimensional? That g2 is such that, so I'm going to put in the derivative with respect to y, which depends now only on g2 because these are fixed. So what's the probability that this dimension is at most 0? So I again want to claim that this is approximately 1. And so what is this now? So in order for this to be 0 dimensional, I need that this polynomial not vanish on any component of this curve. And so, well, okay. And so it's not hard to do. You can bound the probability that this polynomial vanishes on a particular curve. You can show that it's very rare. And you know there are not that many components of this because there are most d components because this thing, in fact, most d minus 1 because this is a polynomial to be d minus 1. So you just add those up and you show that this is it's very rare that when you choose g2 that this new polynomial, this new derivative vanishes on some component. And then finally, you add in the last condition, namely, now you say conditioned on a good choice of these first three, of f0, g1, and g2. What's the probability that h is such that this whole what's the probability that this has no points of high degree, of degree greater than or equal to d over 3? And now you can use, it's the same kind of argument. I mean, now this set here, because it's been good so far, this is going to be a finite set of points. And I can bound the number of points that are here by Bézout's theorem. So, and now for each point, what's the probability that f vanishes at that point? It's pretty rare if that point has high degree. So, so for all the points that have high degree, for most h, it won't vanish there. So you can again show that this is approximately 1. And so now the probability that all this happens is also essentially 1. And that finishes the proof of this claim, which shows that for most f's, there aren't any points, there aren't any singularities of this plane curve. And now, okay, so I guess, yeah, so, well, okay, so end of proof is this. So it's just that the set we wanted is just you take the ones that satisfy the conditions up to R, and you delete the ones that have a singularity of medium degree, and you delete the ones that have a singularity of high degree, and you want to measure the density of this. The density of this is attending to the Euler product we wanted it to, and these things are going to 0. So this is going to the whatever, zeta A2 inverse, zeta 3. And so that proves that P has the density claimed. Okay, so that's the end for today, and next time I'm going to talk about some applications of this theorem and also some other theorems that can be proved using the sieve type of method, and maybe I'll also talk about the arithmetic analog, what's the common generalization of this theorem and the square free integer theorem. Okay, thank you.